All right, we're going to be using my word problem guide. If you need the word problem guide, write me an email, diana.thomas@westpoint.edu, and I will send it to you. This word problem guide was developed by students who were learning how to do word problems. And the important thing is it comes from where students look first, not what I think should come first. And I still kind of, I balk at it, but let's do it. So I'm going to do number 7. You were assigned 3.9 number 6. In my class, we did number 5. So let's do number 7. If you look at number 7, there's 2 numbers in there, 5 and 3. So the first step in the word problem guide is to take the number 5 and explain what it is. It's the radius of a cylindrical tank. And it's always the radius of the cylinder. If you have a Coke can, which I think I have one around here somewhere, maybe not, but we have this Indian pickles. So here's a cylinder. If my husband takes more and more of the pickles out of this jar, I'm not going to get a change in the radius of the jar. That's going to stay fixed. So this is not a freeze frame moment in time. That's what my students used to call it, where we had something changing and all of a sudden you stop the camera and you take a freeze frame. That's not the case here. The 5 meters is always 5 meters. So what we get here is that this is a constant. So this is kind of hard to figure out at the beginning until you see more of these problems, but you'll see when I draw the picture, that's where I like to start. I like to start with drawing the picture. Again, that's not what my students want to do first. They want to look at the numbers. So you'll see when I draw the picture what I'm talking about. Maybe the pickle jar here this is hot stuff. Maybe that explained it. So I'm going to assign a variable to things as we go along. And so we see that R is 5 meters. That's how I'm going to call it. Again, that's not how normally a math professor likes to do things. We like to label our variables after we draw the picture. But let's go with it. I'm going to cut off my picture for a second so that you can just see what's going on. 3 is the next number, 3 meters cubed per minute. The units are super, super important. So this is the rate of water that fills the tank. That's obvious that this is a rate. And what is it a rate of? Well, my clue here is that I get this meter cubed. That's volume. cc's, that's volume. And so it tells me that this rate is dV dt. You might not see that right away. I always look at the units. So the first one's a length. If I had meters squared, it would be an area. If I have meters cubed, it is a volume. And the stuff that you have on the right, that's what you want to keep. I was itching to do this. I was also itching because I have a stress rash, but that's an aside. So I was itching to do this. I want to draw the picture. There's my cylinder. Just so you can see it, this is my cylindrical tank. It is as if I was pouring water into this cylindrical tank. So there's my cylinder, and I'm going to put some stuff on it now. There's my R equals 5 meters, always 5 meters. That's my image of my water coming in. And this water is going to be rising, so dV dt is 3 meters cubed per minute. That's the rate that the water's rising. I see the picture first. I've done this so many times with students. They see the numbers first. So that's why I did what I did. The next thing is we go to the sentence with the question mark. That's the last sentence here. How fast is the height of the water increasing? So I just write that down. That's what I'm looking for. That quantity is a rate because the key word is fast, increasing. Those are trigger words for rate. And so I'm looking for a derivative. I just want to go back to my picture. Height that they're talking about is the height of the water. And I'm looking for dH dt. And that's my variable. It's easier for me to go and deface my picture a little bit more and then think about the 2 things at once, that I'm looking for dH dt. Are there any geometrical equations that have to do with volume of a cylinder? I do remember the volume of a cylinder always. It's pi r squared h. So that's my cylinder. I'm going to put all my information that I collected up. This is the right-hand side of number 1. This is the last problem I did, just looking at what formulas I have. Here's my picture. Here's my R. Here's my what I'm looking for. So I put them all together, and like a puzzle piece, I'm going to assemble. So I'm going to start with usually the equation. So volume is pi r squared h. That's not a freeze frame. If it was a freeze frame, I would plug it in later. So you have a question like this on the concept questions, and it's a little bit hard to dig into the concept questions if you're using my word problem guide. But this is always r squared. If it was a freeze frame moment, I am not allowed to plug in right away. If it's not a freeze frame moment and it's a constant, I'm allowed to plug that puppy in right away. So I'm going to do that. That's 25. So I don't have an r squared. So I'm eliminating that variable. Now, the obvious thing to do, because you're in calculus, is to take the derivative. From left to right, I take the derivatives. dv dt is 25 pi times 1, just a number. It's an ugly number, but it's just a number. Derivative of h is 1, and implicit differentiation says I multiply by dh dt right as I take a derivative of h. So I get 25 pi dh dt. Now, I know that I'm looking for dh dt. So I have to look in my information here. I notice that at the freeze frame moment, I'm not allowed to plug this in earlier because it's a freeze frame moment. It was changing. I have to take the derivative first and then plug in the 3. So at the freeze frame moment, dv dt is 3. So I sub that in and solve for dh dt. I get 3 divided by 25 pi meters per minute. And that's what they were looking for. So I am done. Boom.